So we're going to talk about the fractional composition, which helps us determine how much of a compound is in a particular state. And when we're talking about different states, we're talking about being protonated or deprotonated. And so here we have acetic acid on the left. It has a carboxylic acid functional group, and shown by this bright red hydrogen, and it has a pKa of 4.756. And so you might remember that if the pH is below the pKa, then that proton will stay on there and it'll remain protonated. And so we have that form shown here. However, if the pH is higher than that value, then it can become deprotonated and providing this acetate form. And when the pH is equal to the pKa, you're going to have a 50-50 mixture of both of these forms. And so we can look at the fractional composition shown here on the right. And so it shows the composition on a scale of 0 to 1, 1 being 100%, 0 being none of it, and then the pH along the bottom. And we can see, sure enough, below that pH, we have this red form dominating, which is the carboxylic acid form. After the pH, we have the acetate form that dominates, and it's the principal species. And then at the pKa equal to the, or at the pH that equals the pKa, we have a 50-50 mixture. And so if we look at something that has one extra proton, so we have 2-aminophenol, and it has 2 acidic sites, and so we have the OH from the here, and it's got a pKa of 9.97, but this amine could also be protonated, and it would have a pKa of 4.7. And so again, below both of the pHs, we're going to have both of these sites completely protonated, and so we can see that below 4.7, this form dominates. As the pH increases, that amine becomes deprotonated, and we're left with the 2-aminophenol. And then as the pH increases further above that 9.97, we have the completely deprotonated form of the 2-aminophenol. Whenever our pH equals our pKa, again, we have 50-50 mixture of these two forms, or 50-50 mixture of these two forms. But you can see that this becomes really helpful once we have this becomes more helpful as we have more protons, because we can see the various forms that will exist at different pHs based off of that would see how the composition changes based off of the pH. And so we can do this using these equations that are shown here. We have our sort of generic acid equilibrium equations, where we have our acid interacting with water. It becomes deprotonated, and we generate hydronium, and that just continues for each of our subsequent equilibrium expression or equilibrium reactions. And then at the bottom, we have sort of our generic forms of these fractional compositions. Fractional compositions always shown using this alpha, and then the subscript typically refers to which form you're talking about. And so we're going to use these. Let's go to our next page. So let's say we're going back to our 2-aminophenol. And so again, has two acidic locations. We know the pKa's. We can write out our equilibrium expressions for both of these. And so we have fully deprotonated, interacting with water, producing hydronium, generating the 2-aminophenol, 2-aminophenol, reacting with water, generating hydronium, and producing this completely deprotonated form. And so we have the Ka's that correspond to it. And so we can take one of our generic equations and see how we use it. And so the concentration of our H3O plus, or hydronium, is going to be directly related to the pH. And so if we're going to say that this is happening at pH 4, then our concentration of H3O plus is going to equal 10 to the negative pH. And that's what I've done here. I have 10 to the negative 4 wherever the concentration of H3O plus is. Anytime we need the Ka, again, if we're going from pKa to the equilibrium constant, I'll use this spot right here. Our Ka is equal to 10 to the negative pKa. And so we need Ka1 here, we use Ka1 here. We need Ka2 here, we use Ka2 there. And so we can use these generic equations that to assemble what our fractional composition is going to be. The top portion is what's really going to be changing. The bottom is always going to follow this pattern of starting with your pH, your concentration of your hydronium to the highest number of protons, and then as you're slowly going to decrease this number by 1 and add a Ka, and then until you run out of them, and then eventually you're just going to multiply by all the Kas together. And so it'll take a little bit, but these are very systematic. And so this bottom part is always going to be the same. It's really just the top part's going to change depending on what composition you're looking at. And so once we plug all of this in for the fully protonated form of the 2-aminophenol, we can see that at pH 4, it's still lower than our pKa. We're expecting the protonated form to dominate, and we see that 0.83 of it, or 83% of the composition, is in this fully protonated form. We can look at the other forms and see that, and like I said, this bottom part never changes for any of these. It's this top part that's going to change. For the 2-aminophenol, at pH 4.0, we end up with 0.17 or 17% of the composition being deprotonated. So some of it is deprotonated as we're getting closer to that pKa value. And then finally, our completely deprotonated form, the equation is shown here. Again, that bottom part is not changing. It's just this top part. Our composition is 1.75 times 10 to the negative 7, or essentially it's 0%. There's so little of it. It's essentially 0%.